Okay, Unit 2. Limits. Lecture 2.1. Limits. All right, this is the heart of calculus, right? We talked about this in lecture 1. All of our problems kind of needed this, so now we're going to talk about it. What are we going to talk about? We're going to talk about sequences, we're going to talk about the limits, we're going to talk about divergence patterns, we're going to give examples, and then we're going to talk about the limit clause for sequences. Okay, recall sequences. Okay, I'm just going to say a lot of this because you should have it written already somewhere, and if you don't, let me know. An infinite sequence is a never-ending, ordered list of numbers. In general, it looks something like this. And again, we're going to talk about infinite sequences here. Okay, it never ends, it's ordered, it's a list of numbers. Each of these guys is called a term or element of the sequence. This is called the second term, this is called the third term. The general term, a sub n, is called the nth term, if you start indexing at 1. This n is its index of the term. If you want to, you can abbreviate this thing as something like this, a sub n in some kind of reasonable brackets, from 1 to quote-unquote infinity. Okay? If you think about, I may write down here. If you define f by f at n equals a sub n for all positive integer n, you can see that a sequence is essentially a function whose domain is the positive integers. Okay? So we put positive integers in and we get the bits of the sequence out. And so if we wanted to, we could graph a sequence, okay? So on the x-axis, what would we get? We get the positive integers, 1, 2, 3, 4, and so on. And on this axis, we put the values of the sequence. So a sub 1, the first term, a sub 2, the second term, a sub 3, the third term, and so on. Okay? So the graph doesn't look like a curve anymore, it's just a bunch of points. Okay? Questions? Okay. So there is just such a graph. And this was uploaded at the customary time this morning. Okay, let's look at a few of these values. So this is, the sequence is 1 minus 1 over n. Again, an infinite sequence, so it goes on forever. Let's calculate a few values here. When n equals 1, 1 minus 1 over 1, so 1 minus 1, so 0. There we go, 0. At 2, 1 minus 1 over 2, so 1 minus a half, so a half, and there we go. At 2, we have a half, okay? And so on. And you notice this is tending to something. This is tending to 1, right? As we go on, as the index increases, the values get closer and closer and closer to 1. And why is that happening? Because as n increases, this guy shrinks down to 0, and all you're left with essentially is 1. You get closer and closer and closer to 1. Okay? So for that example, we say that the sequence converges to a limit, let's say the sequence converges and has limit 1. Okay, the sequence converges to the limit 1, the place where it's tending to. Good? Okay. could write the limit as n grows of a sub n, or you could write that expression in there, is 1. Or you could write as n grows, the elements of the sequence tend to 1. Okay? Okay, here's the definition of the limit of a sequence. If the terms of an infinite, this is a really fuzzy definition, by the way. If the terms of an infinite sequence, a1, a2, and so on, tend toward a particular number L, then the sequence converges, or you say it is convergent, and has the limit L. We may write that, kind of like that, or that, kind of like that. If the terms of the sequence do not tend toward any particular number, then we say the sequence diverges or is divergent. Okay? We've talked about this before, but we didn't define it properly, right? We talked about this with the circles, when we approximated the circle area, and we talked about this when we were trying to figure out what an exponential means for an irrational exponent. Okay? So now we're actually defining it, again in a fuzzy way. We're talking about tending toward a particular number. You can think of tending toward as approaches, or settles toward. And I'll give you a hint of the actual proper, precise technical definition of this. I'll come back to this slide. Okay? Here we said the limit was 1. What that actually means is that for any arbitrarily narrow band around that limit, okay, you don't have to know this, okay, this is the precise definition. For any arbitrarily narrow band around that limit, I can find a point along this sequence past which all the values stay in that band. Okay? So I eventually get as close as I want to that limit. And that's the precise definition of a limit. Okay? So by approaches, we actually mean approaches and gets arbitrarily close to it. And like in that example, it's possible for the terms to never actually equal the limit. Okay? They might just approach it, never actually equal it. Okay. Okay, saying that a sequence converges or is convergent is the same as saying that the limit exists. And saying that a sequence diverges or is divergent is the same as saying that the limit does not exist. Does not exist. Okay? So it's one or the other. Okay. Questions? Okay, in that last example we talked about the 1 over n shrinking away to 0 as n increased. Okay? In fact, the limit as n grows of 1 over n to the r is 0 for any positive r. Okay? So we showed the case for 1, and we said that 1 over n shrinks down to 0, but no matter what positive r you've got there, that's going to shrink down to 0 as well. Okay? How can you think of this? Well, we talked about power functions, right? So this should make some sense. If you think about x to the r, okay, x squared, x cubed, all those guys, if you go far enough that way, they're all going to grow without bound, so 1 over them is going to approach 0. Things like the root functions, right? The square roots, they keep growing without bound, so 1 over them is going to approach 0. Does that make sense? Good? Okay. All right. Divergent sequences. There's a movie called This, right? But not called Convergent? Is that right?
Yeah.
Okay. Okay. One second. Okay. We talked about what divergence means there. It means that you don't converge to a particular limit. Now, here's a special case. If the terms in a sequence eventually, and it's always eventually, increase without bound, as n increases, then we write lim as n grows of a sub n is equal to infinity. I'll show an example here. That's not an example. Hey, look, I missed a slide. People, this is an illustration of this fact, okay? So if you're unconvinced of that fact, there's a few examples to show you that 1 over n to the r for r positive is going to approach 0 as n increases. Okay. Okay, so that's what I wanted. Okay, so this guy diverges, right? It is not approaching a particular value as you go this way. It just keeps going up and up and up and up. Okay? And that's a special kind of divergence. Okay? This kind of divergence where you just keep growing. Okay? Growing without bound. That's what this is. So for that guy, you would say this. Okay? You'd say that guy diverges to infinity. Okay? In very heavy quotes and feeling bad because you've said the word infinity. Okay? Okay. Again, this is divergence. Okay? I don't want anyone thinking that this says that the limit exists and is infinity. Okay? The limit does not exist. This thing is divergent. Don't ever say the limit is infinity. Okay? This is a special notation that marks a special pattern of divergence where you grow without bounds. Okay? And again, infinity is not a number. Okay. One reason I picked this is because it gets a bit wavy, and I wanted to make the point that what matters is the eventual behavior of this thing, okay? It doesn't really matter that it did this at the beginning. Once it finally matured and grew up, it grew without bound. And I'll give you again a hint of the technical definition of the limit in this case. You say that you get divergence to infinity when, no matter what level you think of, okay, eventually there's going to come a point where the sequence beats that limit and stays above it forever. Okay? And I won't write out the technical definition, but that's essentially all it is. Okay? Growing without doubt. Okay. Examples. N to the r, where r is positive. We sort of talked about the opposite there, right? We talked about how the reciprocal of that is going to tend to 0. Now we're talking about how it blows up, okay? And then increases. Likewise, any polynomial with positive leading coefficient. Any polynomial with positive leading coefficient, like this guy. Okay, polynomial in n, okay, like this guy. Right, and we've seen that polynomials, so we expect this guy to go up forever. Okay? Again, this is a special pattern of divergence. Questions? Okay. If the terms in a sequence eventually decrease without bound as n increases, we write da equals minus infinity. Okay? So write that down. It says decrease, we write minus infinity. Does that make sense? If you want, I'll write the whole thing out again. We're good so far? Alright. Lots of other divergence patterns are possible, okay? So not all diverging sequences do this blowing up thing. And again, divergence, again, doesn't just mean blowing up. It just means that you do not converge to a particular value or limit. Yes, ma'am?
Only polynomials with what?
I said This always causes problems. Okay, any polynomial with positive, and this is the stupid abbreviation for positive, leading coefficient. Yep. And by leading coefficient, I mean the one on the highest exponent there. And that's a 1, that's positive. Does anyone else write positive like that?
Yeah.
Okay, all right, good. Okay, good. All right. Okay, a few more special examples. Okay, these guys have a range of behaviors that are interesting, so let's look at them. Let's think about the sequence r to the n. Okay, again, n is the index that's increasing, and r is some fixed number. Okay? And this looks awfully exponential, right? We talked about stuff like this, except our n was a continuous thing x, and our r was our positive base b. Okay? And these are just, if you know what this means, discretely sampled version of those curves, right? So you've got the curve, and you just put points at every integer, and you get these guys. Okay? So let's look at what goes on here. Lots of heavy breathing. Okay. And? Okay. If r is greater than 1, that just corresponds to our growing exponential, right? So that guy doesn't converge to a particular value, it just keeps growing without bound, it's divergent, and it's divergent in a particular way, it diverges to infinity. So, to save myself some trouble. Okay. Yeah. Do I want to write this? No, I don't want to write this. Here we go. Lim. As we grow, r to the n diverges to infinity. Okay, exponentials growing, exponentials blow up. Good? Okay. If r is equal to 1, and that's the blue guy there? Yeah, the blue guy there. If r is equal to 1, we've got our stupid boring 1 to the n, which is just constant at 1. So obviously it converges. It converges to that thing that it stays at forever. It just converges to 1. Lim 1. Okay? Diverges to infinity, quote unquote, converges to 1. Okay, look at the red guy. That's a decaying exponential sample. Okay? That's if r is between 0 and 1. And does it converge or no? Yes, to 0. Okay, so if you're between 0 and 1 exclusive, I'm just going to write ditto here, okay? Equals 0. Okay, you shrink down to 0. And you get as close as you could possibly want to 0, if you go far enough along. Okay, the purple guy's another stupid case. It's 0 to the n, which is always 0. So obviously it converges, and it converges to 0. Now, I'm not too fussed about you guys putting this whole thing on your cheat sheets or anything, okay? Just understand what's going on here. Yes, no, not yes, yes, sir.
If you are you allowed to write it like as n approaches infinity, r to the n approaches?
You saw me not do that, right? I think you can. Let's say yes, you can.
Like for if you're writing it for like a problem, you'd say like as x approaches infinity, y approaches infinity.
Yeah, or yeah. So in this case, n approaches infinity. This guy approaches infinity.
Yeah.
Yeah. I try not to say it too much, but yeah, if you write it with the arrows like that, yeah, that makes sense. As far as I'm concerned, if you write it like this or with the as this, then this, that's cool. Yep. Okay, cool? All right. And this just means repeat what I wrote above because I'm too lazy to write it. Okay, questions? Okay, these are the sort of ones we've seen before. This is slightly new now. Okay, this is what happens if we got negative quote-unquote bases. Okay, similar-ish, but with some different behavior, right? If r is less than minus 1, what's going on here? It's the blue guy, it's doing this, right? It's expanding, okay, so it's clearly not going to converge to anything, right? And it's oscillating on either side of 0, okay? So the sign is switching. The sign is switching, and its envelope is expanding. So that's obviously not going to converge. So if r is less than minus 1, it diverges. Okay, because it doesn't go to a particular number. And it's not diverging to infinity or to minus infinity, right? It's bouncing up and down like that. It's not going to either of them, okay? It's not growing without bound, it's not decreasing without bound. It keeps bouncing back and forth, okay? So just say it's divergent. Okay? If you wanted to, you could say its absolute value diverges to infinity. Okay? If r is equal to 1, sorry, if r is equal to minus 1, you just keep bouncing between, which one is it? It's black. You just keep bouncing between minus 1 and plus 1. Okay? Now notice this thing is ordered. It's nice. It's periodic. It's oscillating, but it doesn't converge. Okay? So we can say this guy diverges as well. Exactly. Okay, again, it's periodic. It's oscillatory. It's nice. It only takes two values, but it doesn't go to one particular value, and so the limit doesn't exist. We say it diverges. Okay, and there's no special notation here for that either. Good? And finally, at the risk of writing too low, if we're between minus 1 and 0 exclusive, what are we doing? Again, by analogy to the last thing, and the opposite of the blue guy. We bounce back and forth between positives and negatives, but we shrink. So yes, we converge. Converge to 0. Okay, we get closer and closer and closer, arbitrarily close to 0, while bouncing. Okay, questions about this stuff?
How would we know, like, is it like from the function that we can see that it bounces up and, like, it switches signs?
How do you know?
Yeah, how do you know if it's switching signs? Just by looking at, like, the restriction and, like, without graphing.
If I wrote minus 3 to the n, right? Let's say. If I wrote minus 3 to the n, what happens? What's the first term? It's minus 3 to the 1, so minus 3. If n equals 2, then you get minus 3 squared, which is 9. So notice the sign flip.
Oh, okay.
If you cube it, then you go minus again, right? So whenever you get a minus in the power, this happens. In some cases, if you write, I don't know, sign something with an n, oftentimes that'll give you a lot of bouncing around. Yeah? Does that make sense, though?
Yeah.
Okay. Yeah, just try with minus 1 and do a few terms and you'll see this. Questions? Awesome. Okay. All right. Again, I thought this set was interesting because it does all sorts of behaviors, and they all look sort of the same. It's just that the base is changing. Example. All right, a sub n is equal to 3n cubed plus n squared minus 2n plus 1 over 2n cubed minus n squared minus 3. Okay, and I want you to tell me what's going on. Is this thing converging or diverging? If it's converging, what limit is it converging to? If it's diverging, is it got a special pattern or not? Okay? Anyone know what to do in these kinds of situations? Factor, yeah. Although I didn't even try to factor. Anything else? You're talking about something, you know?
Isn't like the constants
Mm-hmm.
kind of depict where the asymptote is?
That's pretty good. That's pretty good. Okay? Yeah. Okay, and I'll show you the way we do it, or the right way to do it. Okay? That's exactly right. Okay. So, what's this equal to? Divide everything, okay, top and bottom, so nothing changes. Divide everything by the reciprocal of the highest degree term you see here, okay? And I'm going to say the highest degree term you see in the denominator, okay? So in this case, that's n cubed. So divide everything by n cubed, and you'll be okay, right? If you divide top and bottom by the same thing. So divide everything by n cubed, and you've got this. And there's no danger that I'm introducing divisions by 0 here because n is greater than or equal to 1. So again, look for the greatest exponent term in the denominator and divide through by that. And hopefully that's right. Okay? Okay, what happens as n grows up? We talked about all these kinds of things disappeared. Yeah? All these guys shrink to 0. Okay? But these guys stay. Okay, so as n grows, those guys shrink away, and these guys stick around. And so this whole thing tends to 3 over 2. So it converges, and it converges to 3 over 2. Okay? And the reason this happened with this kind of thing, well, look at what's going on here. These are two things that on their own blow up, right? Both of them diverge to infinity, and yet their ratio converges to something nice. Okay? And the reason the ratio converges to something that's both nice and non-zero is that these guys are equal degree polynomials. Okay? And I suspect that's what he meant when he said, is that right? The leading coefficients determine the... Okay. Does that make sense? So while the top and bottom on their own blow up, their ratio converges to something nice. Okay?
Divide by what?
Divide by the largest power of n you see. I would say that you see, but let's say you see in the denominator. Okay, because the two degrees are the same, the highest degree you see here is n cubed, and the highest degree here you see is n cubed. So that's it. Does that make sense? So divide everything by n cubed. Okay? Okay, what else? And if you see things with square roots, sometimes this works as well. So if you see some sort of polynomial inside a square root over something possibly inside a square root, oftentimes you do a similar sort of thing and that helps. Okay? And here's proof. Good? Okay. Ah, you didn't see that. All right. Questions? Okay. Example. Square root of n plus 1 minus the square root of n. And again, tell me the same stuff. Does it converge or diverge? If it diverges, does it do it in a special way? And if it converges, what's its limit? Okay. The trick with these kinds of things, first of all, convince yourself that this isn't trivial, right? Convince yourself that, for instance, as n increases, this guy diverges to infinity and this guy diverges to infinity. You've got now the difference of two things that diverge to infinity, and it's hard to figure out how that would behave. Okay? So you need some semi-intelligent way of figuring this out. And one way is this. Multiply by 1. Very complicated expression for 1. Okay? I haven't changed anything, right? I just multiplied by 1 here because the top and bottom are the same. And what have I done? I've changed this minus to a plus, okay? And if you've dealt with complex numbers and things like that, you'll know that this kind of thing is called the conjugate, okay? So when you take the minus and turn it into a plus, or a plus and turn it into a minus, you call this guy the conjugate of this guy, in some sense. Okay? All right. What's a minus b times a plus b? Excellent, yeah. Oh man, 2 and 1. A plus b is a squared minus b squared. That's difference of squares, yeah? That's exactly what's happening here. So, this times this is just going to be square root of n plus 1 squared, so just n plus 1, minus the square root of n squared, so just n. Okay? Difference of squares. And on the bottom we get that thing. Okay? Alright, n plus 1 minus n, that's just 1. 1 over root n plus 1 plus root n. And now we have it in the form where we can see what's going on. Okay? As n increases, this guy's going to increase without bound, this guy's going to increase without bound, the denominator increases without bound, and the top is some constant. So the whole thing shrinks down to 0. So you get convergence to 0. Does that make sense? Tell me the other question. Yeah? Yeah.
When you solve a problem like this on a test or something, we go through the steps of rationalization, and then we kind of look like we have to apply the limit.
Can you say that one more time?
When we like go through all of the work with the algebra.
What would you do? Would you jump to here?
No. What I'm saying is that on the test, would you like us to show like what it converges at, or should we just put like what it converges?
Oh, so just possibly guessing?
No.
You should, yeah.
Like, do you want us to show that like percentage of okay equals?
Okay, tell me the alternative. And the alternative is to just say,
As opposed to just what you did.
what I did.
It's just for a teacher to see our work. Like,
Oh. So do I want you to write lim whatever equals whatever, rather than this? To be honest, if we ask, does this converge, does this diverge, you should probably write this converges, and if we say what's the limit, you should probably write the limit is 0 in some way. Yeah? If you're short on time, you know what you're going to do, right? Okay. Good? Okay. Alright. And that's that, proof, yeah, the thing goes to 0. Despite the fact that both of the pieces blow up. Okay. By the way, what do we have here? We had a constant over something that grows without bound, and that whole thing therefore goes to 0. If we have a constant, and this is just taking sketchy notation to the limit now. If we have a constant, oh boy. If we have a positive constant over something that goes to, you know what, I won't do this. No, maybe I will do this. Okay. If we have on top a positive constant, and on the bottom something that goes to 0, okay, from the positive side, okay, so it's positive and it goes to 0, this whole thing grows without bound and diverges to infinity. Does that make some sense? So if you've got a positive constant up top, and on the bottom something that's positive but goes to 0, then the whole thing blows up to infinity. Okay? And if you've got a negative constant over that, then it goes to minus infinity. And if you've got a positive constant, and this guy is negative and goes to 0, then you've got divergence to minus infinity. Okay? Do you want me to say that again, or I'll show you sometime? Or just ask me and I'll show you. Okay, just for fun. Who knows what this limit is? As n increases, the limit of 1 plus 1 over n all to the n. And is that E? Yeah, good. E. Okay? Which is cool, man. Okay? Alright, Jacob Bernoulli came up with this. Well, he was talking about compound interest. And you may, if you've done any stuff with interest, you may notice that this is part of the formula for compound interest. Okay, and he was dealing with what happened if you compounded continuously instead of daily or quarterly or whatever. And this kind of thing happens. That thing magically converges to E, that magical E that we talked about, and you guys love to answer at the Mobius. Here's a weirder one, okay? Each term here, again, these are just for fun, okay? Fun! Each term, okay, the nth term, is the sum of the squares of the reciprocals. Let me say that again. The sum of the reciprocals of the squares of the positive integers from 1 all the way through to n, okay? So the first term is just 1 over 1, the second term is 1 over 1 plus 1 over 4, third term is 1 over 1 plus 1 over 4 plus 1 over 9, and so on, okay? What does this thing converge to? Anyone? You can't guess this. And if you can, you shouldn't be here.
0.
What's that? Something unbelievable, okay? We talked about E before, what's the other one? Yeah? What's that? Oh, that's a cool one, but no, this isn't that. Okay, unbelievably, okay, that thing converges to pi squared over 6. Okay, which is madness, right? And Leonhard Euler discovered, this thing used to be called the Basel problem, named after a city in Switzerland, and Leonhard Euler, in his reckless, almost careless, almost wrong, ingenious way, came up with the first proof of this, and then came up with a better one. And there's something on Wikipedia that I think, if you know about infinite series, you can understand. A proof for this. And I think that's just unbelievable that attempts to that. Okay? Okay. And again, the proof is really, really pretty, and if you look at the simple one I looked at, it's also wrong, but only very wrong. It can be filled in. Okay, I just want to close with this. These are the limit laws for sequences. If an and bn are convergent sequences and c is a constant, then you have all these guys. The limit of the sum is the sum of the limits. The limit of a difference is the difference of the limits. If you multiply by a constant, you can bring the constant out. You can bring the constant out. Okay, and all these things mean that what, that this limit is a linear operator, not like log. Okay, again, don't do this kind of thing for log. Okay? Those are those guys. The limit of the product is the product of the limits. And the limit of a quotient is the quotient of the limits, provided you don't divide by 0. Okay? When you apply these things, make sure you check. Don't divide by 0, and make sure you check that these limits actually exist. Okay? Don't try to divide infinities or add infinities or anything like that. Okay? No examples for this. If you want me to give you an example, I can. It's pretty straightforward. Okay, last time I asked you for, or we found this. We found the limit as n grows up of 3n cubed plus n squared minus 2n plus 1 over 2n cubed. You have this from last time. Minus n squared minus 3. Yeah? And this limit winds up existing, and what you do is you divide through by the highest power of n in the denominator. Okay? So you wind up with lim n goes to infinity. 3 plus 1 over n minus 2 over n squared plus 1 over n cubed over 2 minus 1 over n minus 3 over n cubed, one hopes. Okay, and we said what? We said all these guys disappear, and so we're left with 3 over 2. Okay? The way you'd address this properly, using the limit laws, is you'd do this. You'd say, okay, the limit of a quotient is the quotient of the limits, so then you'd write lim, this is about to get very, very painful. 3 plus all that stuff up top, over lim, n goes to infinity, 2 minus all that stuff on the bottom. Okay? And then you'd use the next limit law, which tells you that the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. And that if you have a constant, you can bring the constant out in front of the limit. Okay? And that would allow you to write this like this. Oh boy. Okay, the limit of a constant is just a constant. So if you wanted to write this in full using the limit laws, you'd have to go through this pain. But somewhere in your head, you should be thinking about this anyway. Okay, the limit of a constant is just a constant again. Something like that, plus or minus any errors, okay? And then what do you say? You say that limit's 0, that limit's 0, that limit's 0, that's 0, and that's 0. So all those guys are 0. 3 plus 0 minus 2 times 0 plus 0 is 3. 2 minus 0 minus 3 times 0 is 2. And that's the answer. Okay? Okay, and again, all that's kosher because all those limits existed, and because you didn't try to divide by 0 at any point. Okay? And again, the limit laws tell you the sequences have to converge, okay? So once again, for something like the other example we had, which was something like this, a sub n equals square root of n plus 1 minus square root of n, okay? Someone asked me on Monday, can you just say, well, this guy goes to infinity and that guy goes to infinity, subtract them and you get 0. That's not how anything works, okay? Don't subtract infinities, don't divide them, don't use them, they're not numbers, okay? And the limit laws tell you you can only apply the limit laws if the sequences in question converge. Okay? And if you're writing infinities, they ain't converging. So don't try to deal with them that way. Okay? Which is why we had to find that fancy pants conjugate way of dealing with it. Am I making sense? Am I not making sense? Any questions? Okay. So there's your limit law example, so I don't feel guilty about not giving you. And I think that is it. We will talk about instantaneous velocity next time. Thank you, everybody. Tutorial at 5:30.